Welcome to Impossible But True, 1 hour of mind-blowing scientific facts, where the laws of nature bend, reality surprises, and what seems impossible is actually true. Before we dive in, if you're enjoying these fascinating stories from the frontiers of science, don't forget to like and subscribe. It helps more curious minds discover the wonder of the universe. Chapter 1. The universe is strangely fine-tuned. Have you ever tried to balance something perfectly, like stacking rocks until they don't fall, or turning a radio dial to get the exact frequency of your favorite station? A little too far one way, and it's static. A little too far the other, and it's gone again. That kind of delicate precision is impressive. Now imagine that same idea, but instead of rocks or radio dials, you're tuning the fundamental forces of the universe. And if even one of those dials is off by the tiniest fraction, everything collapses. No galaxies, no stars, no Earth, no life, nothing. This is what scientists mean when they say the universe appears fine-tuned for life. And it's one of the most fascinating, almost unbelievable facts in science. The physical constants of the universe, like the strength of gravity, the speed of light, the mass of particles, seem to be set just right to allow the universe to exist the way it does. But just how just right are we talking? Let's take a look at the force of gravity, weak but crucial. First, consider gravity. We all know it as the force that keeps us grounded on Earth and keeps planets orbiting the sun. But did you know gravity is extremely weak? Compared to the electromagnetic force, gravity is weaker by a factor of 10 to the power of 36. That's a 1 followed by 36 zeros. But even though it's weak, it plays a huge role in the formation of stars, planets, and galaxies. Now here's the mind-bending part. If gravity were just a tiny bit stronger, stars would burn through their fuel much faster. That means they'd live shorter lives, leaving less time for life to evolve. If gravity were a tiny bit weaker, stars might not form at all, or they'd be too cool to kickstart nuclear fusion. Scientists estimate that the strength of gravity must be tuned to within 1 part in 1060 to allow life to exist. That's like tossing a dart at a dartboard, the size of the universe, and hitting a target 1 inch wide. On your first try. The expansion rate of the universe. Let's rewind to the very beginning, the Big Bang. When the universe first exploded into existence, it began expanding, and it's still expanding today. But the rate of expansion had to be just right. If it had expanded just a little bit faster, matter would have spread out too quickly to form galaxies or stars. If it had expanded just a bit slower, gravity would have pulled everything back in, collapsing the universe before it had a chance to evolve. According to physicists, the rate of expansion had to be fine-tuned to 1 part in 10^5. That's an even smaller margin for error than gravity. In practical terms, it's like balancing a pencil on its tip for 13.8 billion years, and it stayed standing. The strong nuclear force. This is the force that holds atomic nuclei together. It's what binds protons and neutrons in atoms. If this force were just 2% stronger, hydrogen, the most basic and abundant element in the universe, wouldn't exist. All hydrogen would have been fused into heavier elements in the early universe. And since stars, water, and life depend on hydrogen, we wouldn't be here. If the strong nuclear force were just 2% weaker, then atomic nuclei wouldn't hold together at all. The universe would consist entirely of hydrogen. No chemistry, no stars, no life. In other words, the strong nuclear force has to be balanced on a razor's edge. And somehow it is. The cosmological constant, the universe's anti-gravity. One of the most baffling pieces of the fine-tuning puzzle is something called the cosmological constant. This constant represents the energy density of empty space, what we often call dark energy. It's responsible for the accelerated expansion of the universe. But here's the twist. It had to be fine-tuned to an even more absurd degree than anything we've mentioned so far. If it were larger, space would expand too rapidly for galaxies to form. If it were smaller, the universe might collapse in on itself. How finely tuned is it? Estimates suggest the cosmological constant had to be adjusted to 1 part in 10. That's a number so big it's almost impossible to imagine. It's the biggest known fine-tuning in physics. The odds of hitting it by chance, astronomically low. So, why is the universe so perfect? These examples are just the beginning. There are dozens of physical constants in nature, and many of them need to be precisely balanced for life to be possible. So the big question is why? There are a few possible answers, and each one is as strange as the question itself. 1. The anthropic principle. This idea says, of course the universe appears fine-tuned for life, because we're here to notice it. If the universe weren't compatible with life, no one would be around to ask the question. So the fact that we exist in a life-friendly universe isn't surprising, it's just selection bias. You can only win the lottery if you bought a ticket, and we're living in the winning ticket. It's a bit like saying it's not surprising that Earth is perfect for humans, because if it weren't, we wouldn't be here talking about it. 2. The multiverse hypothesis. What if our universe isn't the only one? According to the multiverse idea, there could be an enormous or even infinite number of universes, each with different physical constants. Most of these universes would be lifeless and chaotic, but in a few rare ones, everything lines up just right. We live in one of the rare lucky universes, where the constants allow life to emerge. The multiverse doesn't explain why the tuning is perfect, it just says, if enough universes exist, one of them had to get it right. It's like rolling a trillion-sided die. Somewhere someone was bound to roll a perfect one. 3. Design or purpose. Some thinkers propose that the fine-tuning of the universe suggests some kind of design or purpose. Maybe the universe is the way it is, because it was intended to be life-permitting. This idea strays from physics into philosophy or theology, but it remains one of the possible explanations for the universe's improbable perfection. While science can't prove or disprove design, many scientists admit that the fine-tuning question raises deep and meaningful puzzles. What are the odds? To give you a final idea of just how unlikely all this is, imagine every particle in the known universe, protons, neutrons, electrons, all of them. Now imagine that each particle had to roll a dice and all get the same number for life to exist. That's how unlikely this level of fine-tuning is, according to some physicists. And yet it happened. We don't know why. We may never know. But it's one of the most astonishing, almost impossible facts in science. Final thoughts. The universe could have been cold, lifeless and empty, or it could have collapsed before it even began. But somehow everything lined up. The forces of nature, the constants of physics, the chemistry of atoms. It all worked out perfectly. We live in a universe that seems built for stars, planets, oceans, and thinking beings. Whether this is the result of chance, necessity, or something else entirely, is one of the greatest mysteries of existence. But one thing is certain, the fact that we are here to ask the question at all is extraordinary, and that alone is worth marveling at. Chapter 2. Time is relative. Time. It feels like the one constant in our lives. It ticks forward, second by second, minute by minute, hour by hour. Your watch, your phone, your heartbeat, all keep time. We live by it, schedule our days around it, grow old because of it. But what if I told you that time isn't fixed? That time doesn't flow the same way for everyone? That two people can experience two different lengths of time even if they start and end in the same place? As strange as it sounds, this is not science fiction. This is science fact. Welcome to the strange world of relativity. Einstein's big idea. In 1905, a young patent clerk named Albert Einstein proposed something that would change how we see the universe forever. He said that time is not absolute. It doesn't tick at the same rate for everyone. Instead, time is flexible. It stretches. It contracts. This became the basis of Einstein's theory of special relativity, and later, General relativity. Here's the key idea. Time moves more slowly the faster you go. And it also moves more slowly the closer you are to a strong gravitational field. Let's break that down. Time slows down at high speeds. Imagine you have two identical twins. One of them boards a spaceship and travels at nearly the speed of light. The other stays on Earth. When the traveling twin returns home, something incredible has happened. The one who stayed on Earth has aged more. The twin on the spaceship is younger, maybe by years. This isn't a thought experiment. It's been tested, not with people yet, but with atomic clocks. Scientists placed one clock on a fast-moving airplane and kept the other on the ground. After the flight, the moving clock had ticked slightly more slowly. It had literally experienced less time. This phenomenon is called time dilation. At everyday speeds, like driving a car or flying on a plane, the effect is so tiny you'd never notice. But at speeds approaching the speed of light, the effect becomes dramatic. In fact, if you could travel fast enough, you could go on a round trip to a distant star and return to Earth thousands of years in the future, while only a few years passed for you on the ship. Time travel to the future is not just possible, it's baked into the fabric of the universe. Time slows down in gravity too. Now here's the next twist. Gravity affects time. The stronger the gravity, the slower time moves. This is part of Einstein's general theory of relativity, published in 1915. It tells us that massive objects like planets and stars actually bend space and time around them. This bending is what we feel as gravity, and it warps time itself. So if you're standing on the surface of Earth, time moves slightly slower for you than it does for someone floating in space. This isn't theoretical. In fact, the GPS system in your phone wouldn't work if engineers didn't account for time dilation. Satellites orbiting Earth move fast and experience weaker gravity, so their clocks tick faster than clocks on Earth. To make GPS accurate, scientists have to adjust for the difference in time between space and ground. Every time you get directions to a coffee shop, you're using Einstein's relativity. Amazing, isn't it? Near a black hole, time practically stops. Let's take this idea to the extreme. Black holes are regions of space where gravity is unimaginably strong, so strong, not even light can escape. And near a black hole, time slows down dramatically. If you were to hover just outside a black hole, in theory, time for you would nearly stop compared to the outside universe. You could look out and watch the rest of the universe race ahead of you. This concept was portrayed in the movie Interstellar, where astronauts land on a planet near a black hole. Just 1 hour on the surface equals 7 years back on Earth. That's based on real physics and real equations. Time moves slower in gravity. It's not just a plot device, it's how our universe works. So what is time, really? After learning that time isn't constant, that it changes depending on speed and gravity, the question naturally arises: what exactly is time? Surprisingly, scientists don't have a perfect answer. Time is one of the most familiar things we experience, yet also one of the most mysterious. Is it a dimension like space? Is it a flow? Is it an illusion created by memory? Some physicists believe time is just a way of tracking change, a tool that our brains use to organize events. Others think time may not even be fundamental at all, that it could emerge from something deeper in the laws of physics that we don't yet understand. What we do know is this: time is not the simple ticking clock we once thought it was. It bends, stretches and warps. It slows down and speeds up, depending on where you are and how fast you're going. It is in every sense of the word relative. Final thought: so next time you're waiting in line or watching the clock before a meeting, remember, your experience of time is just one version of it. Somewhere right now, time is ticking at a different pace. Maybe on a mountaintop, maybe in orbit, maybe far across the galaxy near a black hole. And that's not science fiction, that's science. Time travel to the future, GPS satellites, black holes warping time, they all point to one impossible truth that is entirely real. Time is not absolute. Time is relative. Chapter 3: Quantum Weirdness. The impossible becomes real at the tiniest scales of existence. We live in a world where cause and effect seem obvious. Drop a ball, and it falls. Flick a light switch, and the bulb glows. These are the laws of classical physics, the rules that govern cars, buildings, rockets, and baseballs. But beneath the surface, at the scale of atoms and subatomic particles, the universe obeys a very different rulebook, one that seems less like science and more like magic. Welcome to the world of quantum mechanics, a world where particles can be in two places at once. Observation changes reality. Objects can influence each other instantly, no matter how far apart they are. Cause and effect become a cloud of probabilities. And yet, despite sounding absurd, quantum mechanics has never been wrong. It's one of the most successful scientific theories ever developed. Let's step into this invisible realm, where the rules of the ordinary dissolve, and discover how the universe really works, no matter how impossible it may seem. The double-slit experiment. When observation changes everything, our first stop in the quantum world is the famous double-slit experiment. Picture this: you're firing tiny particles, electrons, photons, or even atoms, at a screen with two thin slits. Behind the slits is a detector screen to capture where the particles land. When you fire particles one at a time, something bizarre happens. If you don't look at which slit the particle goes through, the final pattern on the screen shows interference, like waves overlapping and cancelling each other out. This is what you'd expect from a wave, not a particle. But as soon as you try to measure which slit the particle actually passed through, the interference pattern vanishes. Instead of a wave pattern, you get two distinct bands, as if the particles had decided to go through one slit or the other, like bullets. So what changed? Only one thing. You tried to observe the path. It's as if the particle knew it was being watched and chose to behave differently. That simple act of observation collapsed the wave of possibilities into a definite outcome. This single experiment shattered our understanding of reality. It tells us that before measurement, particles don't exist in any one place. They exist as probabilities and only solidify when observed. Let that sink in. Reality doesn't fully exist until it's measured. Superposition, the quantum maybe. One of the strangest consequences of quantum mechanics is the concept of superposition. A particle, like an electron or a photon, can exist in multiple states at once. It can spin clockwise and counterclockwise, be here and over there, or even exist and not exist, all at the same time. Think of it like flipping a coin. In our world, the coin is either heads or tails once it lands. But in the quantum world, the coin is both heads and tails until someone looks at it. Only then does it choose a side. This is not just a theory. It's how electrons orbit atoms. It's how quantum computers work. Superposition is a central fact of the quantum world. To dramatize this, physicist Erwin Schrödinger proposed a famous thought experiment, Schrödinger's cat. A cat is sealed inside a box with a vial of poison, triggered by a quantum event, like the decay of a radioactive atom. Until you open the box, the atom is both decayed and not decayed, meaning the cat is both dead and alive. Ridiculous? Yes, but also real, in a quantum sense. Until measured, quantum systems exist in multiple states simultaneously. Superposition is not just possible, it's the default. Entanglement, spooky action at a distance. Now imagine two particles that are created together in a single event, like twins born from the same explosion. These particles can become entangled, meaning their properties are linked, no matter how far apart they go. Change the state of one, and the other changes instantly, even if it's on the other side of the galaxy. Einstein hated this idea. He called it spooky action at a distance. How could one particle affect another faster than the speed of light? That would violate everything Einstein's own theories stood for. But again, experiments prove it's real. entangled particles remain mysteriously connected. Measure one, and the other instantly knows, even if they're separated by light years. This isn't communication in the traditional sense. You can't use entanglement to send messages faster than light, but it does show us that space may not be what we think it is. In some deeper way, the universe may be non-local, connected at a fundamental level beyond our current understanding. 4. The uncertainty principle. Precision is an illusion. In classical physics, we like to think we can measure anything exactly. The speed of a car, the temperature of water, the position of a planet. But at the quantum level, certainty disappears. Heisenberg's uncertainty principle states that you can't precisely know both a particle's position and momentum at the same time. The more you know about where it is, the less you know about how fast it's moving, and vice versa. This is not a flaw in our tool, it's a fundamental property of nature. It tells us that uncertainty is built into the fabric of the universe. At a quantum level, there is no exact, only a range of probabilities. This uncertainty is why electrons don't crash into atomic nuclei. It's why atoms exist at all. It's not a bug, it's the reason matter holds together. 5. Quantum tunneling. Walking through walls. Here's another gem from the quantum world. Quantum tunneling. In classical physics, a particle can't go through a barrier unless it has enough energy. Imagine rolling a ball up a hill. If it doesn't have enough speed, it rolls back down. But in the quantum world, particles can sometimes tunnel through barriers, even if they shouldn't be able to by classical rules. It's as if the ball disappears on one side of the hill and reappears on the other, without climbing it. This isn't rare, it happens all the time. The sun uses quantum tunneling to fuse hydrogen atoms into helium. Without it, the sun wouldn't shine. And we use tunneling in technology too, in tunnel diodes, scanning tunneling microscopes, and the development of quantum chips. 6. Reality. A cloud of probabilities. So what does all this mean? At its heart, quantum mechanics tells us that reality is not made of definite things, but of possibilities. Until something is observed, it exists as a wave of probability, a cloud of maybes, and that raises deep questions. Is there a real world out there when we're not looking? Does consciousness play a role in collapsing the wave function? Are there multiple universes where every possible outcome happens? No one knows the answers for sure. Quantum mechanics gives us the how, not always the why, and it predicts the behavior of atoms, molecules, and light with incredible accuracy. But it also leaves us with profound mysteries about the nature of existence. Final thought: the weirdness that powers the world. You may never directly see a quantum particle. You'll never be both alive and dead, or teleport across the galaxy. But quantum mechanics affects you every second of your life. It's in the GPS satellites that correct for time differences using quantum clocks. It's in the lasers that scan your groceries. It's in the microchips that run your phone, computer, and car. It's the foundation of modern physics, chemistry, and electronics. And yet it remains wildly counterintuitive, a reality stranger than fiction. The quantum world is not just small. It's surreal. It reminds us that the universe is not bound by human logic. It is deeper, stranger, and more wondrous than we can imagine. And as we continue to explore this world, through quantum computing, cryptography, and experiments yet to come, we are just beginning to unlock the secrets of the impossible. Because in the quantum world, weird is normal. Chapter 4. You are made of stardust. The atoms in your body were forged in stars, billions of years before you were born. Have you ever looked up at the night sky and wondered about your place in the universe? Maybe you felt small beneath a blanket of stars. But what if I told you that those distant stars are not just faraway lights? They are part of your origin story. It may sound poetic, but it's scientific fact. You are made of stardust. Not metaphorically, literally. The elements that make up your body, carbon, Oxygen, nitrogen, iron, calcium were all created in the hearts of ancient stars that died long before Earth was even formed. That sounds impossible, but it's true. Let's explore how the cosmos built you. The building blocks of life came from stars. Right now, your body is a swirling system of trillions of atoms, all working in harmony. These atoms are arranged into molecules, which form cells, which make up tissues, which become organs, which together form you. But where did those atoms come from? Hydrogen, the simplest and most abundant element in the universe, was formed just minutes after the Big Bang, about 13.8 billion years ago. It's the same hydrogen that fuels our sun today, but hydrogen alone can't make life. For life, you need heavier elements, like carbon for your cells, nitrogen for your DNA, oxygen for your blood, and iron for your hemoglobin. These elements weren't born in the Big Bang, they were cooked inside stars. Stars are element factory. Through a process called nuclear fusion, stars fuse light atoms into heavier ones. In the core of a star, hydrogen atoms collide and merge to form helium. In bigger stars, that helium fuses into carbon, then oxygen, then silicon, and eventually iron. But there's a catch. Fusion stops at iron. Making anything heavier than iron takes more energy than it gives. And when a star can no longer fuse, it dies. And that's when things get really dramatic. 2. Star death. A creative explosion. When a massive star runs out of fuel, gravity takes over, the core collapses, and the outer layers explode in a violent, blinding event called a supernova. Supernovae are among the most energetic events in the universe. In a few seconds, a single star can outshine an entire galaxy. But more importantly for us, it's in this violent death that the universe creates gold, silver, uranium, and other heavy elements. It's during a supernova that elements heavier than iron are forged, in a split-second crucible of extreme heat and pressure. Those elements are then blasted into space, spreading throughout the galaxy. Over millions of years they mix with clouds of gas and dust, the raw material for new stars and ants. Eventually, some of that dust comes together to form our solar system, and eventually the cosmic recycling system. Think about this for a moment. The iron in your blood, forged in the core of a massive star, the calcium in your bones, created in a long-dead sun, the carbon in your skin and the oxygen in your lungs, produced in stellar furnaces billions of years ago. Every atom in your body, except for hydrogen, has been through at least one star. Some atoms have even passed through multiple generations of stars. The universe is a giant recycling system. Stars are born, live, die, and scatter their ash. From those ashes come new stars, new planets, and new life. You are not separate from the cosmos. You are the cosmos, made conscious and self-aware. 4. How we know this is true. This idea sounds too beautiful to be real. So how do we know it's true? The answer lies in the science of spectroscopy. When light passes through a gas, or is emitted by a star, it carries a fingerprint, a unique spectrum of lines that reveals what elements are present. By analyzing starlight, astronomers can see exactly which elements a star is fusing in its core. They can tell how stars evolve, how they die, and what elements they release. We've observed supernovae, spreading these elements across galaxies. We've detected them in distant interstellar clouds, and we found them in meteorites, leftover building blocks of the early solar system. The chemistry of your body matches the chemistry of the stars. It's not a guess, it's measurable, testable, and repeatable. It's science, time, and scale. Your ancient origins. Let's put this in perspective. The carbon in your cells, probably 6 to 10 billion years old. The oxygen you breathe, older than the Earth itself. The atoms in your body, some of them have traveled across space for eons before finding their way into you. You are ancient in the most literal way possible. When you drink a glass of water, you are sipping molecules older than the planet. When you look in a mirror, You're seeing a structure built from the remnants of stars that lived and died long before our sun was born. Every breath, every heartbeat, every thought, it all happens using atoms with cosmic pedigrees. You are not just in the universe, you are of it. 6. You are stardust with awareness. Here's what makes this even more extraordinary. Stars are not alive. They don't think, they don't know. But somehow, through the vast interplay of energy and gravity, the matter forged in stars came together in just the right way to build neurons and synapses, memory and emotion, the ability to wonder and love and dream. The universe, through you, has become aware of itself. You are stardust that thinks, stardust that asks questions, stardust that ponders its own existence. And there's something deeply humbling and uplifting about that. We often feel small compared to the cosmos. But the truth is, we're not separate from it. We're not just looking at the stars, we are the stars, looking back at themselves. Final thought, the stars in you. Next time you gaze up at the night sky, remember this. You are not just a bystander to the universe. You are a product of. You are connected to every star that has ever shone, every supernova that ever exploded. The atoms that make up your brain were once inside suns. The iron in your blood once flowed through the core of a giant star. You carry the story of the cosmos within you, written not in ink, but in atoms. And that story is still being written, with every heartbeat, every breath, every moment of your life. You are stardust, you are history, you are the universe, made. Chapter 5. Time moves differently in space. Time is not constant. It bends, stretches, and slows down, depending on where you are and how fast you're going. What if I told you that time isn't what you think it is? We treat time as if it's absolute, ticking forward at a steady pace, second by second, minute by minute, the same for everyone, everywhere. But that's not how the universe works. According to Einstein's theory of relativity, time is flexible. It speeds up and slows down depending on gravity and motion. And this isn't science fiction, it's a scientific fact backed by decades of experiments and observations. Let's explore this mind-blowing truth, that time itself is not fixed, but fluid, that someone moving faster than you is aging more slowly, that someone living on top of a mountain is experiencing time a bit faster than someone at sea level. It sounds impossible, but it's real. The idea that changed everything. In the early 1900s, Albert Einstein turned our understanding of time on its head. Before Einstein, most scientists believed in absolute time, the idea that a second is a second, no matter where or how you are. But Einstein proposed something radical. Time is not separate from space. It is part of a larger structure called space-time, and this space-time is shaped by gravity and speed. What does that mean? Let's break it down. Einstein's theory of special relativity says that the faster you move, the slower time passes for you relative to someone at rest. Later, his theory of general relativity added another twist. The stronger the gravity, the slower time moves. So time is not constant, it can stretch and bend. The universe proves this every single day. 2. Time dilation. Speed changes time. Imagine you're on a spaceship traveling near the speed of light. Let's say you take a trip around the galaxy, going at 99.9% the speed of light. For you on the ship, maybe only 5 years pass, but when you return to Earth, you find that 500 years have passed here. You haven't traveled through time in a machine. Time itself has slowed down for you, because you were moving so fast. This is called time dilation. It's not a theory anymore, it's a measured reality. In fact, we see it with astronauts. When astronauts spend time in orbit, moving at thousands of kilometers per hour, they experience time a little bit slower than people on Earth. It's only milliseconds, but it's real. Their clocks tick slightly different. Their biological processes slow down ever so slightly. If you lived on the International Space Station for a year, you'd be a few milliseconds younger than someone who stayed on Earth. Tiny differences, but imagine what happens at much higher speeds. 3. Slows time too. Speed isn't the only thing that affects time, gravity does too. According to general relativity, the stronger the gravitational field, the slower time moves. This is because gravity bends space-time, and time flows more slowly in regions where space-time is more curved. Here's an example. Time moves slightly faster on the top of a mountain than it does at sea level. That sounds ridiculous, but it's true and measurable. In 2010, scientists at the National Institute of Standards and Technology in Colorado conducted an experiment with two extremely precise atomic clocks. They placed one clock just 33 centimeters higher than the other. The result, the higher clock ticked faster than the lower one. Even that tiny difference in elevation, barely more than a foot, caused a detectable difference in the flow of time. 4. GPS. Proof in your pocket. This isn't just abstract theory. It affects your everyday life. Every time you use GPS, whether you're finding directions on your phone or tracking a package, you're relying on Einstein's theory of relativity. GPS satellites orbit the Earth at an altitude of about 20. Because they are farther from Earth's surface, they experience weaker gravity, and therefore, time moves faster for them compared to us. But they're also moving at high speeds, which slows their clocks down. Engineers must account for both effects, the gravity difference and the speed, to keep GPS systems accurate. If they didn't, your GPS location would drift by about 10 kilometers each day. So every time you get directions to a coffee shop or check your location on a map, you're using a system that only works because we understand how time bends and stretches in space. 5. The twin paradox. To make this even more dramatic, physicists use a thought experiment called the twin paradox. Imagine two identical twins. One stays on Earth, the other travels on a spaceship at near light speed to a distant star and back. When the traveling twin returns, they find that their sibling is much older, perhaps decades older, while they've aged only a few years. Both twins are healthy. Nothing went wrong. Time simply passed more slowly for the one who traveled at extreme speed. This isn't just a paradox, it's a prediction of relativity, and it's been confirmed with particle accelerators, where subatomic particles moving near light speed live longer than they normally would. 6. Can we travel to the future? Here's where things get really interesting. If you can slow down your experience of time by traveling at near light speed, then in a sense you can travel into the future. You can't go back in time, but you can jump ahead by moving fast enough or staying near a massive object like a black hole. In fact, near the edge of a black hole, time slows down dramatically. If you orbited close to a black hole and returned to Earth, you might find that centuries had passed here, while only hours passed for you. It sounds like science fiction, but it's grounded in real physics. Final thought: time is not what it seems. We grow up thinking of time as a universal constant, a river flowing steadily forward. But the truth is far more complex. Time is woven into the fabric of the universe, and that fabric bends, stretches, and warps under the influence of speed and gravity. Time is personal, time is relative, and in a very real way, the faster you move, the slower you age. The farther you are from gravity, the faster your clock ticks. We don't live in a clockwork universe. We live in a relativistic one, a universe where time is not absolute, but deeply tied to the motion and mass of everything around it. So the next time you look at your watch, remember that little ticking sound is not the same for everyone. Out there in space, clocks tick differently, and so do hearts. Chapter 6. There's more empty space in matter than matter itself. Everything around you and inside you that feels solid is in reality mostly empty space. At first, this might sound like some kind of philosophical or spiritual idea, the kind of metaphor you'd hear in a poem or a meditation. But this is a hard scientific fact. Every object you see, every surface you touch, every inch of your body is mostly empty space. This is not an exaggeration or a poetic way to say we're all connected. It is the literal physical truth revealed by decades of atomic and quantum physics research. 1. The atom. More empty space than stuff. Everything you know is made of atoms, the fundamental units of matter. The word atom means indivisible in Greek, because early philosophers thought atoms were the smallest possible building blocks. But atoms themselves are made of smaller particles, a nucleus and electrons. The nucleus contains protons and neutrons packed tightly together, forming the dense core of the atom. Surrounding the nucleus is an electron cloud, electrons that zip around in a mostly empty space. If you imagine the atom scaled up to the size of a baseball stadium, the nucleus would be a tiny marble sitting on the 50-yard line. The electrons would be buzzing in the upper seats. The rest, empty space. This means the majority of an atom's volume is actually empty space. In fact, over 99.99999999999999999999999999999% of an atom's volume is empty space. That's mind-boggling. 2. How can we be solid if we're mostly empty? Here's the natural question. If atoms are mostly empty space, why do things feel solid? Why don't we fall through floors? Why don't our hands pass through tables? The answer lies in the behavior of electrons and the fundamental forces of nature. Electrons carry a negative electric charge. When two atoms come close, the electrons in one atom repel the electrons in the other. This repulsion creates a kind of invisible barrier that prevents the atoms from collapsing into each other. This force is what makes matter feel solid. So when you touch a table, you aren't touching solid matter, as you might imagine it. You're actually feeling the electromagnetic force pushing back, the electric fields of electrons preventing your hand from merging with the table. This force is so strong that it holds everything apart, despite all the empty space. The quantum world, where nothing is what it seems. The story gets even stranger when we consider quantum mechanics, the branch of physics that governs the behavior of particles on the smallest scales. Particles like electrons don't behave like tiny billiard balls. They behave like waves, existing in a cloud of probabilities. Because of this, electrons don't have precise locations. They are smeared out in space, creating a probability cloud around the nucleus. This cloud isn't empty, it's a fuzzy region where you might find an electron. This is why electrons don't simply crash into the nucleus. Their wave-like nature keeps them spread out. It's this quantum fuzziness that gives matter its shape and volume, even though the particles themselves are tiny points surrounded by mostly empty space. What if you compressed the empty space? What if you could remove all the empty space between particles and pack matter as tightly as possible? The result would be astounding. Your entire body, every atom compressed into pure nuclear matter, would shrink from its current size to something about the size of a sugar cube. Think about that for a moment. All 8 billion people on Earth compressed this way could fit into a sugar cube. The reason this is possible is that the nucleus of an atom is incredibly dense, composed mostly of neutrons and protons packed so tightly they nearly The only place this kind of density naturally occurs is in neutron stars, the remnants of exploded massive stars, crushed by gravity until the atoms collapse and the electrons combine with protons. Neutron star matter is so dense that a single teaspoon weighs more than all the cars on Earth combined. How quantum mechanics makes solid things possible. The reason matter holds together, and why it doesn't collapse into itself, is due to a fundamental principle called the Pauli exclusion principle. This principle states that no two identical fermions, particles like electrons, protons, or neutrons, can occupy the same quantum state simultaneously. Think of it as a cosmic no overcrowding rule. Because of this, electrons are forced to occupy different energy levels or orbitals around the nucleus. This layering creates structure and volume. Together with electromagnetic forces, the Pauli exclusion principle prevents matter from collapsing and gives it a stable size. The illusion of solidity. This leads to a profound realization. What you feel as solidity is really a complex dance of forces and quantum rules. We don't experience the emptiness because the forces at play give us resistance, a pushback, which we interpret as solid. Without these forces, matter would be no more than a ghost, diffuse and intangible. 7. Strange phenomena arising from empty space. Quantum mechanics also tells us that particles sometimes behave in ways that defy classical intuition. For example, there's a phenomenon called quantum tunneling. Particles have a tiny chance to tunnel through barriers that classical physics says they shouldn't be able to cross. While this doesn't happen in everyday life at human scales, it's crucial for things like the sun's energy production and modern electronics. The very idea that particles can appear in places they shouldn't be, just by probabilistic magic, shows how strange and non-intuitive the world of empty space and quantum fields really is. Implications for how we see ourselves. Understanding that matter is mostly empty challenges our everyday perceptions. You are not a solid block of stuff, but a vast collection of particles held apart by forces, dancing in a sea of emptiness. Your skin, your muscles, your bones, all composed mostly of empty space. Yet this empty space is filled with energy and governed by rules that create the stability needed for life to exist. This perspective opens doors to awe and wonder. We live in a universe where what feels solid and real is underpinned by emptiness and invisible forces. Final thought. Emptiness as the foundation of everything. This emptiness is not a void, it's a canvas on which the universe paints reality. Without empty space, atoms wouldn't exist, chemistry wouldn't work, and life as we know it wouldn't be possible. So next time you touch something solid or look in the mirror, remember, you are mostly empty space, but that emptiness is the foundation of your existence. And that fact is as beautiful as it is mind-blowing. Chapter 7. Quantum particles can be in two places at once. Prepare to have your understanding of reality shaken. At the tiniest scales, particles can literally exist in two places at the same time. The unbelievable quantum superposition. Imagine standing in your living room and suddenly finding yourself not just there but also on the other side of the room at the exact same time. Sounds impossible, right? For the everyday objects you know, chairs, cars, people, this never happens. But for quantum particles, the fundamental building blocks of matter and light, this strange phenomenon is real and well documented. This phenomenon is known as quantum superposition. In classical physics, a particle always has a definite position and state, but in quantum mechanics, particles don't have fixed positions or states until they're observed. Instead, they exist in a superposition, simultaneously occupying multiple states or locations, described mathematically by a wave function. The double-slit experiment, where particles become waves. The best way to understand superposition is through the double-slit experiment, one of the most famous and elegant demonstrations of quantum strangeness. Here's how it works. A beam of particles, usually photons, particles of light, or electrons, is fired at a barrier with two tiny slits. On the other side of the barrier is a detector screen that records where particles land. If particles behaved like tiny bullets, you'd expect two bright lines on the detector, corresponding to particles passing through either slit, but the result is astonishing. Instead of two lines, an interference pattern emerges, a series of light and dark bands typical of waves interfering with each other. This means that each particle behaves like a wave that passes through both slits at once, interfering with itself, until it lands as a single localized particle on the detector. Even more baffling, when scientists place detectors at the slits to see which slit the particle actually goes through, the interference pattern disappears, and the particles behave like classical particles again. This demonstrates the observer effect. Simply observing the particle forces it into a definite state, collapsing the superposition. Through Schrödinger's cat, the paradox of life and death. To highlight just how weird this is, physicist Erwin Schrödinger proposed a famous thought experiment in. He imagined a cat sealed inside a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers and breaks the vial, killing the cat. If the atom does not decay, the cat remains alive. According to quantum mechanics, before you open the box, the atom exists in a superposition of decayed and undecayed states. So the cat is simultaneously alive and dead. Only when you open the box and observe does the wave function collapse, and the cat becomes either alive or dead. While this is a thought experiment, no cats were harmed. It illustrates the puzzling idea that quantum superpositions apply even to macroscopic objects in principle. 4. Why don't we see superpositions in daily life? If quantum particles can be in multiple places at once, why don't we see everyday objects doing this? The answer lies in a process called decoherence. Quantum systems are extremely sensitive to their environment. Interactions with air molecules, photons, or other particles cause the fragile superpositions to collapse almost instantly. In other words, large objects quickly lose their quantum behavior and behave classically. That's why your chair isn't floating in two places at once, and why you don't see yourself split into two. 5. The weirdness of quantum entanglement, closely related to superposition, is quantum entanglement, where particles become linked, so that the state of one instantly influences the state of another, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it challenges our understanding of space and information transfer. Entanglement and superposition together create a quantum reality utterly different from everyday experience. Quantum computing, harnessing superposition. Quantum superposition isn't just weird, it's powerful. Quantum computers leverage this property to represent both 0 and 1 simultaneously with quantum bits, or qubit. This ability allows quantum computers to process vast amounts of information in parallel, solving problems that would take classical computers millions of years. Researchers are racing to build practical quantum computers, promising breakthroughs in cryptography, medicine, and materials science. 7. The many worlds interpretation. Multiple realities. One interpretation of quantum mechanics, called the many worlds interpretation, takes superposition seriously in a radical way. It suggests that every time a quantum event with multiple outcomes occurs, the universe splits into multiple branches, one for each possible outcome. In this view, you are in multiple places at once, but in different parallel universes. While still speculative, this interpretation offers a way to understand superposition without wave function collapse. 8. Experimental confirmation. Quantum superposition isn't just theoretical. Experiments with larger and larger molecules, even tiny viruses, have shown interference patterns. Scientists have pushed the boundary of quantum weirdness from tiny particles to complex systems, confirming that superposition is a fundamental feature of reality. What this means for our understanding of reality. Quantum superposition forces us to rethink what it means for something to exist, or to be somewhere. The classical idea of a single definite reality breaks down. Instead, reality at its core is a cloud of probabilities, a symphony of possibilities, that only crystallizes into certainty upon observation. This challenges our deepest intuitions about identity, location, and causality. Final thought, embracing the quantum mystery. The fact that particles can be in two places at once invites us to embrace mystery and uncertainty. It reminds us that the universe operates on rules far beyond our everyday experience. Yet, these bizarre rules give rise to the complexity and beauty of the world around us. Quantum superposition is not just a curiosity, it's a profound truth about the nature of existence itself. Chapter 8. Time can move backwards in some situations. We all experience time in one direction, from the past to the future. But in the strange realm of physics, there are scenarios where time might just run in reverse. 1. Our everyday experience of time. Let's begin with something simple. Drop a glass on the floor, it shatters. But the reverse, watching shards jump back together into a whole glass, that never happens. This one-way flow of time, from order to disorder, is something we call the arrow of time. It's tied to a fundamental principle in physics, entropy. the measure of disorder in a system. According to the second law of thermodynamics, entropy always increases. Systems naturally evolve from order to chaos, not the other way around. 2. Time's arrow and entropy. Think of a deck of cards. You shuffle it. The order becomes random. But what if you watch the shuffle in reverse? The cards would unshuffle into a perfect order. Possible? Yes. Likely? No. That's because there's an overwhelming number of ways to be disordered, and very few ways to be ordered. So entropy increases, and that increase gives time its forward direction. But here's where things get strange. The fundamental laws of physics don't care which direction time runs. The laws of physics are time symmetric. If you were to film two particles colliding and then play the video backwards, you couldn't tell which version was the original, because Newton's laws, Einstein's equations, and even quantum mechanics work the same way whether time moves forward or backward. This means, in theory, time could run in reverse. So why don't we see it? 4. Time reversal in quantum mechanics. In the quantum world, things get even stranger. The Schrödinger equation, which governs how quantum systems evolve, is also time reversible. This opens up the possibility of particles rewinding through time under certain controlled conditions. In fact, in 2019, researchers managed to simulate a kind of time reversal in the quantum computer. They used a specially designed algorithm to make a quantum state go back to an earlier form. But this wasn't real time travel. It was a demonstration of quantum reversibility. Still, it suggests that under the hood, time might be more flexible than we think. 5. Antimatter, the mirror image of matter. Physicist Richard Feynman proposed a bold idea. What if antimatter is actually matter traveling backward in time? That's right. According to some interpretations of quantum field theory, positrons, the antimatter version of electrons, can be thought of as electrons moving backward in time. This isn't just a mathematical trick. In the equations, the reversal of time and the reversal of charge seem deeply connected. So antimatter might not just be the opposite of matter. It might be our first glimpse at backward time motion. Wormholes and closed time loops. General relativity, Einstein's theory of gravity, also allows for solutions where time could loop back on itself. These are called closed time-like curves, paths through space-time that circle back to the same moment in time, like a cosmic loop. Some scientists speculate that wormholes, tunnels connecting different parts of space-time, could allow time travel. If one end of a wormhole moves differently in time than the other, stepping through might let you move backward in time. But wormholes are purely theoretical. We haven't observed them, and keeping one stable would require exotic matter we've never seen. Still, physics doesn't rule them out. 7. Reversing time in a simulation. Computer models have also revealed that in a perfectly isolated system, time can run backward. Imagine a few atoms bouncing around in a simulation with no external interference. Under the right conditions, their paths can reverse, and the system can unwind itself. This doesn't happen in real life, because no system is perfectly isolated, but it shows how time reversal is theoretically possible. The universe's birth and time's direction. Some physicists believe that the arrow of time began with the Big Bang, when the universe was in a state of very low entropy. But if that's true, what about the far side of the Big Bang? There are theories suggesting that another universe could exist before the Big Bang, where time runs in reverse. A mirror universe moving backward relative to ours. In that model, both universes expand away from the Big Bang in opposite time direction. It's speculative, but fascinating. 9. Could we ever experience time running backwards? In everyday life, the odds are astronomically low. Time's arrow is tied to entropy, and reversing it would require a complete reversal of all atomic motions, a near impossible feat on macroscopic scale. But in controlled environments, in equations, and maybe in deep space, time might not be so rigid. It might bend, it might even rewind. Final thought, time is not what it seems. Time seems straightforward, past, present, future. But physics tells us it's not that simple. In certain scenarios, especially on quantum and cosmic scales, time can behave in ways that defy common sense. It might slow down, speed up, stop, or even run backward. The universe, once again, invites us to question everything we thought we knew. Time, it seems, is not a river, it's a mystery,